And yes, thank you for inviting me. It's really great to talk about the things that we're doing at NORCE and UIB in CCS, especially when it comes to gigaton scale CO2 storage. My name is Eileen Gasda. I am a research director at NORCE. I head up a group of computational geoscientists who we were just talking about. Many of them have had their education from University of Bergen. And I also have a few hats. In addition to, I head up a research center of a so-called Petra Center of Sustainable Subsurface Resources. And I also have a Professor 2 position at the Institute for Physics and Technology, where I teach in the reservoir physics group at the University of Bergen. Okay. I am here to talk a little bit about the things that we will be doing in the new FME, gigaCCS. This is a research and innovation center that was recently awarded in 2024 that will be starting up in 2025. It's a brand new center, but of course it builds on 16 years of CCS research centers led by SINTEF, in addition to a research center some years back led by CMR. gigaCCS, which is just now starting, we had our kickoff meeting last couple weeks ago, is probably now by far the largest research center within CCS of all the FMEs. It is astounding actually how much interest there is. We have 39 partners, 9 research partners, several international partners, and a lot of industry. And of course, as many large centers, has a quite large budget and 8-year timeline, and plans to educate many PhDs and master's students within the broad area of CCS. And those of you know about CCS, the CCS stands for carbon capture and storage. And so the center concept really reflects the so-called value chain of CCS, all from everything from the capture, with more focus on carbon dioxide removal technologies, in addition to the traditional capture technologies and how to make them more competitive. The infrastructure, so the transport part, both looking at ship transport and all of the different facilities and making sure they are prepared for the gigaton scale that is coming. Down into the subsurface and the storage, which I'll talk more about a little bit later, and then looking at the entire chain and how to bring about a very large efforts into CCS moving forward. It's led by SINTEF. The director, Mona Melvik, has a long experience in leading CCS centers, accompanied by her team. And in Trondheim, and then the mission areas. So each of these 4 packages led by different people. And you can see here I am leading in the storage. And then we have the university contacts. And here you see on Norrbotten University of Bergen, who's the main contact from UIB side. I mentioned the partners. It is really impressive, the number of both from power industry and energy companies, in addition to a wide variety of vendors, supply chain, and other organizations that have seen CCS as a growing business and want to be in on the research that's coming to help bring about the large scales. On the research side is also bigger than ever, in the sense of the number of organizations in Norway that are participating from the research side. And so it really is a true national team of CCS researchers, in addition to a few selected international collaborators. But I want to take a step back into where we are and what we know about CO2 storage. I think we were talking about Northern Lights a second ago, that this is not an unknown technology. We've been studying it for a number of years, in addition to quite a few projects. I think on total about 28 different types of projects all around the world have been piloting and up to industrial scale CO2 storage now for going on almost 30 years. So it's a well understood, from the storage side, a very well understood system. And this is something that my colleagues at University of Bergen, Martin Ferne and Jan Norrbotten, have developed a really innovative way of using, bench scale or lab scale, the so-called fluid flower, to really visualize and show how it could quite look if we were able to see to this level of detail underground of CO2 migrating after it's injected. It's a light fluid. It will rise to the top of the storage formation and be trapped underneath some capillary and permeability seals. And over time, it will slowly dissolve into the resident fluid, typically a salty brine, and be slowly transformed into dissolved CO2, which will slowly sink downwards into the. And we can see all this because we can use pH indicators to show where the CO2 is dissolved. CO2, when it dissolves, becomes a carbonic acid, changes the pH. And you can read all about this in a new special issue about the fluid flower and the types of capabilities and benchmarking of tools we've been able to achieve. And about the tools and the modeling and simulation tools, this is very near and dear to my work in my group, and together with our colleagues at the University of Bergen also, but SINTEF and Equinor, you know, and a whole team of people have managed now to really validate the simulators, what I'm showing here on the right. Not exactly a one-to-one situation of what the lab scale, but the point is that in the community of people who do modeling and simulation of CO2 storage, there's a general agreement on how to represent these physics in the modeling tools. And really, it's been quite a lot of achievements recently on making the tools faster, making them more reliable so they can be used in industry settings, a lot more functionality that industry is used to. But the other thing is that they're open source, which means that they're accessible for everybody. And I think this is a really important aspect moving forward, that the CCS industry is not going to be a huge money maker, so we need to make sure we use the most efficient ways of performing these types of simulations. And just so you see, this is showing a simulation using OPM, which is a tool that we've been developing at NORCE together with SINTEF and Equinor, showing the tracking the plume, both the mobile phase and also the dissolved CO2 over time. And you can see how it grows as the plume slowly transforms from being a gaseous fluid into a dissolved phase. So from this sort of knowledge base, we have to start to think about, okay, what's coming forward, what's coming, and the role of CCS in both preventing detrimental climate change and carbon mitigation, but also the role of CCS within the larger perspective of the Sustainable Development Goals. I think we can't forget that anything we do now has to meet a lot of different criteria. From the very classic illustrative model pathways by IPCC, 3 out of 4 heavily rely on CCS in some way, shape, or form in order to meet the 2-degree scenario, right? So it's not just a theoretical thing now. This is something that, unless we are really willing to tolerate immense cuts in energy consumption, which is the first pathway, CCS will be part of the picture moving forward. And not just part of the picture in terms of abating emissions from industry and power, but also, as you see, these curves here all need to go negative into the end of the century, which means we need to be pulling CO2 out of the atmosphere, either by bioenergy with CCS or other forms of direct carbon capture and carbon removal. So this is and the more we wait, the more CO2 needs to be pulled directly out of the atmosphere. And I think the most important part is that this involves a tremendous scale up. I mean, it's something we know how to do, but now we have to do it really quickly and at much larger scale than we have done to date. We have to also make sure that we are protecting life below water, life on land. There cannot be impacts, and we need to have good monitoring. But I think the third thing here is something that we often forget, that there has to be economy here. There has to be a viable business model. There has to be, these companies that do this have to be profitable. And this full package here is something that I think now we move into with gigaton scale CCS. We can't just look at one without thinking about the other two. We mentioned Northern Lights. This, of course, is the first flagship CCS project in Norway, but it's also one of several that are underway or nearly underway. It's part of the Longship project, which is Norway's largest ever climate infrastructure project. They will have up to, and I now see that they have had the final investment decision on the last of the 5 million ton capacity that they have in their first phase. But we have to remember that these storage site and facilities and everything is in a way over-dimensioned for phase-in of new sources, with anticipating up to 20 million tons a year by 2035. So these are large numbers, and these are important. Still a drop in the bucket, but it's still an important milestone. We also have to remember this is heavily state subsidized. It's essentially an infrastructure project at the base of it. And it needs to be fully commercial. That was the stipulation from the government. So the 20 billion, 25 billion kroner price tag, which is the 80% public financing, was contingent on the fact that this needs to be profitable after that first phase. And profit is an important thing here, so we have to keep that in mind. So if you look at the big picture on a global basis, really CO2 storage, given the experience we have, these goals are very ambitious. And if we're going to do it, we need to make sure we're really on the right path now, because it'll be hard to catch up. What I'm showing you here are the anticipated storage volumes on an annual basis from 2020 onwards to 2025, both future expected volumes and also past historic both capture and CO2 stored. So in this green area here is cumulative CO2 stored. At the writing of this paper in 2023, it was 197 million tons, so around 200 million tons have been stored to date, which is a great achievement, I add, although still quite small in terms of several orders of magnitude smaller than what the IPCC scenarios, 1.5 degree scenarios, anticipate as being required of CCS. So we're talking on the order of thousands of millions of tons of CO2 per year by mid-century, which would imply an annual growth rate of around 20%. We are historically at around 7.1. So although this is good, it's growing, it's still going quite slow. But the good news is that because of this 200 million tons that's been stored, it's successful, right? We know how to do it. There's plenty of storage space. There's no technical bottlenecks, but it's about getting things off the ground more quickly. It takes many years to make these investment decisions. Northern Lights, which was awarded public financing in 2020. Now we're in 2025 with the last of the million tons committed, right? So it's 1 year per million tons. You can do the math. That's too slow, right? We need hundreds of these types of multi-megaton projects need to come online by 2050. And again, if you do the math, that would be a couple Northern Lights scale projects online every single year now for the next 25 years. No, 4, right? Those are big numbers. It takes a lot to get these projects up and running. Okay, so I mentioned that there's ample storage space. Oops, sorry, these are just a quick map view of the different kinds of basins that exist offshore, only a small fraction of which have oil and gas, right? The rest of it is available for other things, right? So there's a lot of space out there. And we see a lot of activity. There are now 13 awarded licenses. Only one is which is the Northern Lights license, which is at exploitation. The rest are at exploration phase. But regardless, this is still 13 more than we had 5 years ago. But they're still a long way from final investment decision. And what really comes down to now is, can we make the techno-economics work? And we have to remember that a good region will attract a lot of interest. And you can see already there's quite a lot of clustering going on. And this is good because then they can share above ground infrastructure, but it also implies that some of them will need to be sharing the subsurface aquifer system. And we know that sharing infrastructure makes a lot of sense from economies of scale, but are there unforeseen commercial consequences of sharing these aquifers? And that's really what a lot of the work we've been doing now for the past couple of years and we'll do in gigaCCS is really about. And why is this a challenge? Because in the subsurface, what you have is that you get pressure buildup from injection, right? You would put a large volume of stuff into the ground and it will pressurize that system. And you get pressure plumes, which are the dotted lines, which are larger than the actual CO2 plumes, which are these yellow blobs here. This is just a schematic, but it gives you the idea that the pressure footprint will be much larger and move much more quickly than the CO2 footprint. And we often worry about the CO2 footprint. Oh, we don't want leakage. We want to make sure it's safe. We want to get solved all the fluid flow business. But when you talk about sharing of aquifers, it's about the pressure. And you get an accumulation of this elevated pressure well beyond what they call the licensed acreage, which would be a kind of arbitrary box within which they need to keep the CO2 plume. But no one really, well, not no one talks about the pressure, but it's the pressure that will cause a little bit of headaches, right? But the other part about the pressure is that it's a challenge to understand and manage this because you have to coordinate now among different competing actors. And this competition for storage business adds kind of a twist that is both, interesting from that policy side, but also really relies on our understanding of the physics at these scales and the geology. So that's really what the projects that we're working on now are really about. Getting a good handle on these very large systems is really important moving forward. So we've had, and now together with University of Bergen, in addition to other partners, including 3 companies that are operating, for example, Equinor Northern Lights are in Equinor and Shell are in the Northern Lights Consortium. Harbor Energy has part of 3, maybe 4 licenses of these 13, where we are looking at this, how the conflicting interests on a limited resource, what type of research we can do to help bring us closer to good outcomes. We have been focusing on the Horda platform. This is a large aquifer system called the Troll Regional Aquifer, not to be confused with the Troll giant gas field that now produces 25% of Europe's natural gas. Not that one. It's in the vicinity, but it's not the same system. And this is showing you how a simulation would show the accumulated pressure, which is the red color, due to multiple different wells injecting CO2, different, for example, let's just say fictitious licenses, although there are 3 licenses that are sharing the space, the Luna, the Aurora, which is the Northern Lights, and the Smeaheia. So this is a real system with real potential for pressure interference that we are studying in the Express project. But it's within the context of minimizing the environmental, minimizing the geochemical risk, because as you elevate pressure, you can see these black lines here. These are what they are called modeled faults, so the faults that are inherent to this geology that could be potential risk of either seismicity or leakage. And also the sort of how the policies would maybe work out if we were to maybe start from scratch with this aquifer. But just keep in mind there are already licenses that have been awarded here. And I want to give you an example of how this, what we call race for pressure space, kind of would look like, right? So you have to remember, let me just go back for a second. This outline here, this polygon, is a real aquifer that has real boundaries, right? So it's not an infinite amount of space for pressure to kind of dissipate around, right? So there's a finite resource. And when you have 3, let's say fictitious in this case, wells that are competing for space, which means capacity, which means money, there will be trade-offs, right? They will get in each other's way. And if one outweighs the other, then it can take away from the other 2, right? So there's no win-win, but there are trade-offs, and quantifying these trade-offs is really, really important. So we just look at a very simple system, not the Troll aquifer, but this is another real aquifer, but not in a. There were no anticipated storage licenses here in the Bjarmeland formation. When everybody works together and coordinates and tries to optimize the amount of storage capacity of the entire aquifer, meaning that they appropriately inject the right amount such that the aquifer is maximized with the amount of storage. Then you get a situation where these three companies will inject so much CO2 up to, in this case, 125 million tons, which individually is less than what they would have injected if they were all by themselves in this aquifer, right? So, for example, this yellow guy here wouldn't get 69 million tons injected compared to 76 if nobody else was around, right? If there was no competition. So you can look at it that way, but if you put in a competitive aspect here, and we call this game theory, right? So it's a competitive game theory, cooperative game theory, and you start to play around with, okay, what if yellow guys' priorities were yellow guys' objectives were prioritized? Then that agent would start to outcompete the others for space. And you can see already what happens, right? They may get a little bit more CO2 in, so their yellow bar increases, but then at the sacrifice of the other two who are still trying to play, right? And the only way that the blue or the red can get anything out of this is if they go in a collaboration with the yellow one, right? Because the yellow gets prioritized, and either because they lobbied for more space or whatever, right? But it just shows you that it's really important, and the only reason we get these numbers is because we do mathematical modeling, we do the full multi-objective optimization, and lots of different technicalities here. But the point is that you have to do this in order to really see and quantify these trade-offs. So this is kind of the basis for all the things we're doing moving forward, is that, what kind of research do we need to do to support what we would call a societal positive outcome for these large aquifers, right? And that we think of them from a policy of compromise and make this compromise sufficiently attractive for all parties. So if I go back to this case here, right, is it worth it for Agent 3 to get just a few more tons of CO2 in there at the expense of the entire region? And would there be policies that would sort of encourage a little bit of compromise, right? Which would be to the benefit of others, a slight detriment to the yellow guy, but certainly to the benefit of climate, because you get more into this space. So it's really about understanding, how can we screen these aquifers? How can we make better informed decisions based on the knowledge we have? What kind of knowledge do we need? And should we take a hard look at these aquifers that are out there and fast track the ones where the trade-offs are minimal, right? Where you don't get this really zero-sum game where everybody loses and only one guy wins. They're certainly not going to be the case in all situations, and we can probably screen aquifers in this way. But every geological system is very complex, very unique, and it takes a lot of effort. Those quick slide I showed you now a second ago involved 60,000 simulations and a particular mathematical framework. I mean, it's not ABC here, but it can be done, I think. And I think it's really about using a center like gigaCCS to really look at these challenges, which are, again, for a very known technology like CCS, it's really about this. It's really about sorting out how we can make commercially viable decision-making that is good for the climate and also good for the environment, in the sense that we aren't doing any further damage, right? So all of these simulations I showed you in a second ago are really about still preserving reducing the environmental and societal impact. Okay, so just, like I said, the FME and gigaCCS has only just started. Of course, we have a lot, I didn't show you here. So we have, of all the partners involved, research partners, a majority of them are involved in storage, which just goes to show you the amount of competence we have in Norway, which is clearly logical from the long history with oil and gas, that there's quite a lot of competence in storage from all disciplines. So geology, geophysics, reservoir physics, chemistry, mechanics, modeling, simulation, and you name it. And now, of course, a lot of data-driven AI, which of course comes into play here, as it should, are coming together in this quite comprehensive called mission area in storage. We have a lot of ambitions, and I don't, of course, won't have time to talk about all this. I just want to talk about what we'll do in this called regional storage scale-up. But just keep in mind that, we have a whole work package on digitalization, which is really how you use deep learning, machine learning, and other of these more data-driven tools to accelerate the workflows, right? There's a really time-intensive thing in developing good geological models and dealing with a lot of the geophysical data that comes out of it. So that just just so you know, there's a lot of work going on there. And then and also a lot of work going on in the next generation type of storage. So a lot of what we know now is established knowledge tends to be limited to certain types of geology, which is fine. There's plenty of that geology out there, but there's other types of geology that needs to be understood. And so there's another work package on sort of more challenging things. But I just wanted to talk a little bit about this regional storage scale up, which is where quite a lot of our effort will go. And it will be about looking at a new aquifer system. And I mentioned before how we can sort of fast-track aquifers and do good screening, comprehensive study of these aquifers. Here we'll look at the so-called Frigg-Heimdal, which has been a very productive system for oil and gas. The Frigg gas field, which went out of production a few years back, was one of the largest, for Norway. So there's a lot of production of oil and gas in this region. So we know it has good properties. I mentioned the Troll before. This was the other one we looked at, which we still do. But here we'll focus on this one. And it's a different kind of system. It's an interconnected system of so-called submarine sand deposits that are kind of overlapping sand that actually came in from the Shetland region. So in fact, this aquifer extends over to the UK side, which is very interesting for understanding how two different countries will share an aquifer system. And so this will be, and also where there are 4 awarded storage licenses, and there's a good potential for a lot more here. So what we want to do in gigaCCS is really put a lot of effort into a good model of this system and use it also as a playground for demoing things we're doing, how you kind of build out a even larger knowledge base on very large systems and how they respond, and how we manage and how we plan and how we do these things. So with the last couple of minutes, I'll talk about what NORCE and University of Bergen will do in this particular work package. And this builds out of the Express project, which we have ongoing right now, looking at the Troll aquifer and looking at how we take these very large and relatively, let's say geologically still complex system and think about how to take those pressure dynamics that are happening at very large scales and propagate them downwards onto a region of interest, right? You might have a storage license that is sitting here in the middle here, which is just a small little domain within a very large system where there's lots of things going on, and how you can transfer that very valuable, let's say, dynamic data that's happening out here onto your little area. I mean, not so little, but still a smaller, more finer scale model. So things we've been working on together with the University of Bergen at NORCE has been about this information propagation between the scales. And there's more technical stuff I'll go through here. But what we found in this Express project is that we've come up with a nice mathematically resilient way of preserving both worlds, right? You have physics that are going on at a very large scale, but at the very small scale, you might be worried about a fault that has a risk of producing some seismicity, right? And the scale of that fault is much smaller than the scale of that system, but what happens at that big system will matter for what you do here. So transferring of information back and forth is really important, and we've managed to come up with a relatively seamless way of doing this for pressure. But now we want to talk about geomechanics. We want to think about the deformation. We want to think about the more definitely heavier computational-wise physics involved in geomechanical and stress modeling. So NORCE will look again a little bit more at the engineering side of how you get these tools to really do what the mathematics tells is possible. And University of Bergen in the math department, applied math in the porous media group, will again delve a bit more into the details of how we really look at this cumulative poroelastic deformation from multiple sites with the right kind of mathematics. So that's what we have to look forward to. But like I said, we have kicked off the center just a couple of weeks ago. And the PhD student, for example, that will work in gigaCCS has not even been hired yet. So we anticipate really good results, and I anticipate good collaboration with industry on this, because they're very, very keen to get some answers about how these large aquifers will really work out when so many people have a vested interest in it. So I'll just finish up with just saying that there's a lot we know, but this gigaton scale really poses some different kinds of questions to what would be, generally speaking, a very well-established technology. And I think it's about this collaboration. Well, we've seen already how important public investments are for getting to gigaton scale, at least getting the kicking off in the right direction. We have a lot of good tools and knowledge, and it's really about how we can use that and leverage all that knowledge to look at these very large systems, really uncover these challenges, which aren't just technical anymore. It's how to help everybody operate in a good way, for the benefit of the commercial outcomes, but also the climate outcomes. And coming from a mathematics and numerics background, I think it's a really important part of this, obviously, but so is many other things. You know, in a very fast way, didn't mention that, you know, NORCE, for example, has a fiber optic technology that will help monitor. I mean, all this kind of getting data is really important for refining our understanding of these systems if we're going to be able to say meaningful things, right? So it's more than just the mathematics and numerics, but without the mathematics and numerics, then we would be hard pressed to understand these very, very large systems. So with that, I will take questions and just, of course, acknowledge all of the people who have been working on these things together with us, and that everything we do code-wise is published open source, and you're more than welcome to peruse the repositories at your leisure. So thank you.